Hello and welcome everybody to today's video lecture, which is going to be on Divergent Series. Now that's actually a very big topic, so we're going to limit our focus in this lecture to how Leonhard Euler approached Divergent Series. We'll talk a little bit about Niels Henrik Abel as well, but this is really a tribute to Leonhard Euler and his discovery that divergent series could be assigned in a certain generalized sense a sum. So here's the plan for today's video. We're not going to do an overview of all of Euler's work on divergent series, but we will show how he approached the topic of specific divergent series of the form 1 to the n minus 2 to the n plus 3 to the n minus 4 to the n and so on, where n is a positive integer. And more concretely, we'll show how Euler devised a method to assign a generalized notion of sum, and please note here that I put sum in quotation marks, to these series, even though they're known to diverge. So let's begin this discussion with a motivating idea. Let's consider the series 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, and so on. So this series actually has a name. It's known as Grandi's series. Grandi was the mathematician who first made the proposal about what this series should equal, which was carried forward by Euler. But before we get to that, let's not lose sight of the fact that this series diverges. It diverges because the definition of convergence is that the partial sums of the series approach a limit. But here, the partial sums of the series don't approach any limit at all. They oscillate. To see this, let's just look. The first partial sum, which would only be the first term, I'll call that partial sum S1. That just equals 1. Next partial sum, S2, which is just the sum of the first two terms in the series, that would be 1 minus 1, so S2 just equals 0. The third partial sum, S3, is going to be 1 minus 1 plus 1, which just equals 1 again. And the next partial sum after that, S4, just equals 0 again, and so on. So rather than approach a limit, we see that the partial sums of Grandi's series just kind of bounce back and forth between 1 and 0 forever. But Grandi says, okay, hold on. Even though this series doesn't meet our definition of convergence, thinking heuristically or speaking heuristically about this series, if this is an unending tug of war between partial sums equal to 0 and partial sums equal to 1, and in fact, we have approximately as many partial sums equaling 0 as we have equaling 1. What value would we assign to this series if we were to just call it a draw? If I were to graph what these partial sums are oscillating around, so S sub 1 equals 1, S sub 2 equals 0, S sub 3 equals 1, S sub 4 equals 0, S sub 5 equals 1, S sub 6 equals 0, and so on, what number are these partial sums oscillating around? Well, they're oscillating around 1/2. So even though Grandi's series diverges, the partial sums don't approach a limit, nonetheless the partial sums are doing something very interesting. They're oscillating around the value 1/2. And so in some more generalized sense, we would like to say that the sum, we would like to define the sum of Grandi's series to be equal, and I'll put equal in quotes here, but equal to 1/2. It turns out that there are many different justifications for a value of 1/2 to Grandi's series, and we'll look at how Euler approached this series and drew a similar conclusion. So to see how Euler approached the problem, let's start with the geometric series. Consider the following. We know that for all x such that the absolute value of x is less than 1, then the function 1 over 1 minus x is equal to the infinite series 1 plus x squared plus x cubed plus x to the fourth, and so on. And then if we substitute negative x in place of x in this series expression, then we have 1 over 1 minus negative x equals 1 over 1 plus x, which would then equal 1 plus negative x squared plus negative x cubed plus negative x to the fourth, and so on. And now, of course, negative 1 to any odd power is still negative 1, while negative 1 to any even power becomes positive 1. So then we get that 1 over 1 plus x equals 1 minus x plus x squared minus x cubed plus x to the fourth, and so on. So this is our series expression for 1 over 1 plus x, convergent whenever the absolute value of x is strictly less than 1. And Euler asks the question, well, okay, that's our series expression for 1 over 1 plus x, and it only converges when the absolute value of x is less than 1. But if we define our function this way, saying f of x equals 1 over 1 plus x, what do we get if we take the limit as x approaches 1 from the left side? Well, then we have the left-sided limit as x approaches 1 for the function f of x. That equals 1 over 1 plus 1, which of course equals 1/2. And then looking at the series, if we were to let x approach the limit 1 from the left-hand side there, we would have that 1/2 equals, here I'll put it in quotation marks because again the series diverges at the point that x equals 1, but nonetheless substituting in 1 for x we have that 1/2 equals, quote unquote, 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. The key observation that Euler is making here is that at the boundary of the interval of convergence for this series, 1 minus x plus x squared minus x cubed and so on, at that boundary where x is equal to 1, the series diverges. I'm not denying that in any way here. Notwithstanding that, the function that the series represents within the interval approaches a finite value at the boundary. Namely, the function that the infinite series represents within the interval of convergence approaches the value 1/2 right at the boundary, right where the series begins to diverge. Well, how do we interpret this mathematical phenomenon? Well, Euler writes, it is necessary to give the word sum, quote unquote, a more extended meaning. We understand the sum to be the numerical value or analytical relationship, which is arrived at according to principles of analysis that generate the same series for which we seek the sum. That's Euler writing in 1768. So we'll see how Euler's idea of an extended meaning for the idea of the sum of an infinite series is implemented in what follows, because Euler realized that this approach that he took to Grandi's series could be applied equally well to any divergent series of the form 1 to the n minus 2 to the n plus 3 to the n minus 4 to the n plus 5 to the n and so on, where n is a positive integer. So in order to proceed, we need some necessary background from analysis, which is as follows. If we have a power series of the form c sub 0 times x to the 0 plus c sub 1 times x to the 1 plus c sub 2 times x squared plus dot dot dot, which can be written more concisely as the sum from n equals 0 to infinity of the terms c sub n times x to the n, then the convergence of the power series generally depends on our variable x, right? The coefficients c sub n are just constants here, so it's really x that determines the convergence. So we call the set of values for x over which the series converges the interval of convergence. And in fact, we have already seen for our geometric series 1 plus x squared plus x cubed plus dot dot dot, and the alternating version of that series, 1 minus x plus x squared minus x cubed plus x to the 4th, and so on, we already saw that the interval of convergence for both of those series is x such that the absolute value of x is less than 1. In other words, all points x lying between the endpoints -1 and +1 exclusive. Now, if a function f of x can be represented by a power series within that series' interval of convergence, which is to say f of x equals the power series c sub 0 times x to the 0 plus c sub 1 times x to the 1 plus c sub 2 times x squared plus c sub 3 times x cubed plus dot 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 for all x such that the absolute value of x is less than r, where r is equal to our interval, or in the field of complex analysis, radius of convergence. Then, and here's the important result from analysis, f of x is both continuous and differentiable, and we can determine f prime of x by differentiating the power series. So f prime of x will equal, in this instance, 0 plus 1 times c sub 1 times x to the 0 plus 2 times c sub 2 times x to the first. I'm just applying the power rule to all of these terms, plus 3 times c sub 3 times x squared plus dot dot dot. More concisely, f prime of x will equal the sum from n equals 0 to infinity of terms of the form n times c sub n times x to the n minus 1. And importantly, this series representation of f prime of x will have the same interval of convergence as the series representing f of x. Now, given the above results from analysis, we can extend Euler's reasoning as follows. We already know that for all x such that the absolute value of x is less than 1, the function 1 over 1 plus x can be represented by the infinite series 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth plus dot 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 minus dot dot dot. So for reasons that I hope will become very apparent in a moment, the first thing we want to do here is multiply both sides of this equation by x. When we do that, we get x over 1 plus x equals x minus x squared plus x cubed minus x to the fourth plus x to the fifth minus x to the sixth plus dot 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 minus dot dot dot. Now for the viewers who are paying very close attention to the details of this derivation, I just want to point out that multiplying the series by x does not change its radius of convergence, because by the root test, this series is still convergent for all x such that the absolute value of x is less than 1. But we also know that differentiating this function and its associated series doesn't change the interval of convergence either. So we know on the open interval from -1 to 1 that the derivative of the function x over 1 plus x is equal to the derivative of the series x minus x squared plus x cubed minus x to the fourth and so on. Well, to compute this derivative on the left-hand side of the equation, I need to apply the quotient rule. So I have, by the quotient rule, that the derivative of x over 1 plus x equals the denominator 1 plus x times the derivative of the numerator, which is just 1, minus the numerator, which again is x, times the derivative of the denominator, which in this instance is going to be 0 plus 1, all over the denominator squared, so all over quantity 1 plus x squared. And on the interval of convergence, this function is going to be represented by the derivative of the series above. So it's going to be equal to, just applying the power rule to all of these terms, 1 minus 2 times x to the first plus 3 times x squared minus 4 times x cubed plus 5 times x to the fourth minus dot 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 plus dot dot dot. Well, when I simplify the left-hand side of this equation here, I have 1 plus x minus x, which just equals 1. So I get 1 over the quantity 1 plus x squared equals this series. And now for the final step, we'll take the limit on both sides of this equation as x approaches 1 from the left. And if we do that, we have the limit as x approaches 1 from the left for the function 1 over the quantity 1 plus x squared equals 1 over the quantity 1 plus 1 squared, which equals 1 over 2 squared, or 1/4. And now we know that the series diverges when we set x equal to 1, but nonetheless we can define this finite value 1/4 to be equal, and I put it in quotes, equal in our generalized sense to the value of the series 1 minus 2 times 1 to the first power plus 3 times 1 squared minus 4 times 1 cubed, and so on. And now the number 1 raised to any power just equals 1. So we get that 1/4 equals the quote-unquote sum, the generalized sum of the series 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus dot 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 minus dot dot dot. So to summarize, so far we found that in a generalized sense, the series 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot 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 minus dot dot dot, which does diverge, nonetheless can reasonably be assigned a generalized sum equal to 1/2. That's why I've written the quotation marks around the equal sign. I don't want to give the impression that this series in any rigorous sense converges. Similarly, we found that for the series 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus dot 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 minus dot dot dot, that this series can reasonably be assigned the value 1/4 for its generalized sum. So let's continue this line of reasoning to find the generalized sum for the series 1 squared minus 2 squared plus 3 squared minus 4 squared plus 5 squared minus 6 squared plus dot 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 minus dot dot dot. In fact, to make everything consistent, we should write the above series, which we've assigned the value 1/4, we should write that series as 1 to the first power minus 2 to the first power plus 3 to the first power minus 4 to the first power, and so on. And for the series to which we assigned the value 1/2, we should rewrite that series as 1 to the 0 minus 2 to the 0 plus 3 to the 0, and so on. Now, to advance the argument further, I'll remind you that we've already shown that the function 1 over 1 plus x squared can be represented by the series 1 minus 2 times x to the first plus 3 times x squared minus 4 times x cubed plus 5 times x to the fourth minus dot 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 plus dot 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 in that region of convergence where the absolute value of x is less than 1. So as before, we're going to multiply both sides by x. And when we do that, we get the function x over 1 plus x quantity squared equals x minus 2x squared plus 3x cubed minus 4x to the fourth plus 5x to the fifth minus dot 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 plus dot dot dot. And now let's see what happens when we differentiate both sides. Well, I'll do the left-hand side first on its own page. We have d dx of the function x over the quantity 1 plus x squared equals. So, applying the quotient rule, we have that this derivative equals the denominator, 1 plus x quantity squared, times the derivative of the numerator, which is just 1, minus the numerator x times the derivative of the denominator, which is 2 times the quantity 1 plus x now raised to the first power times 1, all over the denominator squared. So all over the quantity 1 plus x squared, squared again. So simplifying this just equals the quantity 1 plus x squared minus 2x times the quantity 1 plus x all over 1 plus x quantity to the fourth. And then when we multiply out these expressions in the numerator, we have 1 plus 2x plus x squared minus 2x squared all over 1 plus x quantity to the fourth. So those two x terms in the numerator cancel. And so then I have a plus x squared and a minus 2x squared, so I'm left with the numerator equaling 1 minus x squared all over 1 plus x quantity to the fourth. So the numerator is actually the difference of two squares, so I can factor it as 1 plus x times 1 minus x, and that's all over 1 plus x quantity to the fourth. So the 1 plus x term cancels from the numerator, and I can reduce the exponent in the denominator to 3. So I'm finally left with this derivative equaling 1 minus x all over 1 plus x quantity cubed. So let me bring that back to the previous page here. We have the derivative of x over 1 plus x quantity squared equals the function 1 minus x over the quantity 1 plus x cubed. And we can set that equal to the derivative of the series on the right-hand side. So just applying the power rule here, we have that this equals 1 minus 2 times x to the first, plus 3 times x squared, minus 4 times x cubed, plus 5 times x to the fourth, minus dot 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 plus dot dot dot. So now I'll just combine terms together. I have that the function 1 minus x all over the quantity 1 plus x cubed equals 1 minus 2 squared times x to the first, plus 3 squared times x squared, minus 4 squared times x cubed, plus 5 squared times x to the fourth, minus dot 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 plus dot dot dot, again for all x such that the absolute value of x is less than 1. So then when we take the limit as x approaches 1 from the left, by the way, I'm always approaching 1 from the left here because the series already diverges for any values of x greater than 1. We get that the limit as x approaches 1 from the left for the function 1 minus x all over the quantity 1 plus x cubed equals 1 minus 1 all over 1 plus 1 quantity cubed, which equals 0 over 2 cubed, or 0 over 8, which of course is just 0. So now when we take the limit in our series, now obviously the series actually diverges, but if we set x equal to 1 here, we get 0 equals, in our generalized sense, 1 minus 2 squared times 1 to the first, plus 3 squared times 1 squared, minus 4 squared times 1 cubed, plus 5 squared times 1 to the fourth, minus dot 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 plus dot dot dot. the 1's raised to exponents just cancel out, and we're left with 0 equaling, in some generalized sense, 1 minus 2 squared plus 3 squared minus 4 squared plus 5 squared minus 6 squared plus dot 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 minus dot dot dot. All right, let's do just one more. We'll find the generalized sum for the series 1 cubed minus 2 cubed plus 3 cubed minus 4 cubed plus 5 cubed minus 6 cubed plus dot 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 minus dot dot dot. Now we've already shown for all x such that the absolute value of x is less than 1 that the function 1 minus x all over the quantity 1 plus x cubed can be represented by the series 1 minus 2 squared times x to the first plus 3 squared times x squared minus 4 squared times x cubed plus 5 squared times x to the fourth minus dot 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 plus dot dot dot. And now the procedure should be familiar. We'll multiply both sides of this equation by x, and so we get x minus x squared all over 1 plus x quantity cubed equals x minus 2 squared times x squared plus 3 squared times x cubed minus 4 squared times x to the fourth plus 5 squared times x to the fifth minus dot 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 plus dot dot dot. And now we can differentiate both sides, and again I'll show the derivative of the left-hand side of the equation on its own page. So we want to find d dx of the function x minus x squared all over the quantity 1 plus x cubed. So applying the quotient rule, this derivative will equal the denominator of the function 1 plus x quantity cubed times the derivative of the numerator, so times 1 minus 2x, close parenthesis, minus the numerator, x minus x squared, close parenthesis, times the derivative of the denominator, so times 3 times the quantity 1 plus x squared times 1, all over the denominator squared, so all over the expression 1 plus x quantity cubed squared. So we can start to simplify this expression a little bit by noting that in both terms in the numerator I have the quantity 1 plus x raised to a power, so I can cancel a 1 plus x squared from both of those terms in the numerator, and I can reduce the exponent of the denominator from 6 to 4. And so I end up with this expression equaling 1 plus x, close parenthesis, times 1 minus 2x, close parenthesis, minus 3 times the expression x minus x squared, all over the quantity 1 plus x raised to the fourth power. And now when I expand the terms in the numerator, I have 1 plus x minus 2x squared minus 3x plus 3x squared, all over the quantity 1 plus x to the fourth. And now combining like terms, this expression equals 1 minus 4x plus x squared, all over the quantity 1 plus x to the fourth. So I'll bring that result back to our previous page. We found that the derivative of the function x minus x squared all over the quantity 1 plus x cubed equals 1 minus 4x plus x squared all over the quantity 1 plus x to the fourth. Then on the interval of convergence, where the absolute value of x is less than 1, this function is equal to the derivative of the series above. So it is equal to 1 minus 2 cubed times x to the first plus 3 cubed times x squared minus 4 cubed times x cubed plus 5 cubed times x to the fourth minus dot 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 plus dot dot dot. So then we know what to do. We take the limit as x approaches 1 from the left of the function 1 minus 4x plus x squared all over the quantity 1 plus x to the fourth. And so we find that this limit equals 1 minus 4 times 1 plus 1 squared all over the quantity 1 plus 1 to the fourth. And this equals negative 2 over 2 to the fourth, which is negative 1 over 8. So then when we substitute 1 into our series, the series becomes divergent, but nonetheless we can assign the value negative 1/8 to the series 1 minus 2 cubed times 1 to the first plus 3 cubed times 1 squared minus 4 cubed times 1 cubed plus 5 cubed times 1 to the fourth minus dot 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 plus dot dot dot. And then the 1's all cancel, so we're left with negative 1/8 being equal, in some generalized sense, to the divergent series 1 minus 2 cubed plus 3 cubed minus 4 cubed plus 5 cubed minus 6 cubed plus dot 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 minus dot dot dot. So I've just compiled here all of the results that we've calculated so far. These are really Euler's discovery, and he continued this analysis to find the following. And here I'll just point out a few interesting patterns, that the values that are assigned to all of these divergent series are rational numbers, that with the exception of the very first series, which has the zero exponent, the values assigned to all of the series with even exponents equals 0, and that the values assigned to all of the series with odd exponents alternate signs. If some of you who are viewing this are noticing that those patterns are the same ones that we saw for the Bernoulli numbers, you can rest assured that that's no coincidence, but that's a topic for another lecture. So while these results are quite staggering, they might also make us feel a little bit queasy. The rigorous mathematician in all of us might be asking what's really going on here. Euler's approach to summing divergent series was more or less intuitive. So his method of summing series of the form 1 to the n minus 2 to the n plus 3 to the n minus 4 to the n and so on required some rigorous basis, which would be provided later on by Niels Henrik Abel. And so the method actually now takes his name, and it's known as Abel summation or the Abel summability method. And the summability method is based on an important theorem from analysis which Abel proved. We're not going to give the proof here, but I am going to state it. This is Abel's theorem, which says that if we're given a series, the sum of all terms a sub k from k equals 0 to infinity, and we know that that series converges, and if there's a function f of x which can be represented by the power series, which has as its coefficients the terms a sub k, so in other words the power series from k equals 0 to infinity of the terms a sub k times x to the k, and this power series converges for all x such that the absolute value of x is less than 1, then what do you think happens as we take the limit of this function as x approaches 1 from the left? This equals the limit as x approaches 1 for the power series with coefficients a sub k, and as x gets closer and closer to 1, the terms x to the k get closer and closer to 1. And so the sum of this power series gets closer and closer to the sum of the convergence series of terms a sub k. And this might be the result that we expected, but in mathematics, thinking that something is true or believing that something should be true is a very far cry from actually proving it. And so it was Abel who was able to prove this result, and it does take some difficulty to prove it, so he gets the credit. And in fact, Abel's theorem is a very useful theorem. So let's apply Abel's theorem to find the sum of a series that we know to converge where we may not be certain of what the series converges to. And the series that I have in mind is the alternating harmonic series, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus ... plus ... We know that this series converges by the alternating series test. Well, to be more precise, it converges conditionally. But the question here is, what does this series actually converge to? Well, what else do we know? We know that the function 1 over 1 plus x can be represented by the power series 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth plus ... minus ... for all x such that the absolute value of x is less than 1. Now we can integrate both sides of this equation to find that the integral of 1 over 1 plus x dx equals the integral of the series dx, and the integral of the function 1 over 1 plus x is just the logarithm of 1 plus x, so this equals, now integrating term by term, x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus x to the fifth over 5 minus ... plus ... So integrating doesn't change the interval convergence here either, and so we have that the logarithm of 1 plus x can be represented by this series where x is restricted to lying between -1 and 1 exclusive. And so it turns out that this series can be written more concisely as the sum of terms indexed from k equals 0 to infinity of -1 to the k over k plus 1 times x to the k plus 1. And here's the important thing to realize. The leading coefficients of all these x terms just form the alternating harmonic series. So we know that the series of the coefficient terms converges. So then by Abel's theorem, we know that the limit as x approaches 1 from the left-hand side of the logarithm of 1 plus x, which of course is just log of 2, that this equals the sum of the coefficient series. In other words, the sum from k equals 0 to infinity of negative 1 to the k over k plus 1. That's just the alternating harmonic series again. In other words, we know that log of 2 equals 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus ... plus ... So what does Abel's theorem have to do with Abel's summability method for divergent series? Well, Abel's theorem tells us that if a power series, which can be written as the sum from n equals 0 to infinity of a sub n, or here I'm writing c sub n times x to the n, represents some function f of x and converges within the open interval from negative 1 to 1, then if the series still converges also at the boundary at x equals 1, the value it converges to is what we would expect. It converges to f of 1. And in a sense, Abel's summability method sits on top of the foundation of Abel's theorem, because the summability method tells us that if a power series, which can be written as the sum from n equals 0 to infinity of the terms c sub n times x to the n, if that power series represents some function f of x within the open interval from negative 1 to 1, but the series diverges at x equals 1, we can reasonably assign to the divergent series a numerical value, a generalized sum, if you will, equal to the value of f of x at x equals 1, equal to f of 1. One of the reasons Abel's summability method is so appealing is that for series that are known to converge, it gives us back the value for the series that we would expect, whereas we can apply it to many series that would diverge, and it will assign to those series a value that is reasonable. Now, importantly, not every series is Abel summable, but that's a discussion for another time. The important point here, however, is that Euler's work on assigning sums to divergent series was way ahead of its time. It anticipated Abel's summability method by several decades. Well, that's it for today. Thank you so much for watching this video, and if you enjoyed it, please like or subscribe to my channel. Thanks again.